Hmm, just um, just making this one bestie right now on the video conference. Yeah, but I don't know. Well, I wish we never broke up. It was for the better. Wish we were able to talk it out before breaking up. Because that still has a little nothing. I just like how one fest he changed his background to Dunder Mifflin Paper Company. So you heard about that I said it when I thought I meant it but didn't? Who knows? Maybe I did mean it. I thought I didn't, but I did. You're forgetting I'm insecure about my feelings, right? I don't know, but
Mark, why are you sideways?
I don't. Well, my computer broke, so I'm on my phone right now. I can't figure out how to mute myself either. I'm working on it. I'm trying to. Oh, there it goes.
I can mute you. So if you want to talk, maybe kind of go like that, and I'll unmute you. How's that?
Okay, I figured out how to mute myself, so I think we're good.
Oh, okay. Gonna start here in about a minute.
Kevin, what's up, buddy?
Okay, I'm going to go ahead and get started. So I'm going to be doing attendance differently this time because it didn't work out the way I wanted to last time. So everybody's going to have to do the SWIC, but the SWIC's going to be pretty easy. It's just simply going to be saying which, it's going to ask you what the answers were for only the ones we go over. So don't put all the answers in because we probably won't get through all of them. And you have to put in the exact answers that we all agreed on, okay? So I'm just gonna go ahead and give you the code then. So the first one is lowercase a, then uppercase R, then lowercase w. The number is 141, then lowercase d, and then the at symbol, like in your email, the ampersand, I think is what they call it, the at symbol. It's the at symbol, and then the number 5. So there's there's 9 digits there. All right, so today we're gonna be whiteboarding the Ampere's law worksheet, and I don't know how far you guys got on it, if you got that far, so I don't know how far we'll get. The very first one kind of looked like this.
Kenzie.
Okay, so for this, we're trying to figure out the regions in which there might be some points where there's zero net magnetic field. So in order to solve this, you'd have to use the right-hand rule for both of these wires and figure out, where it's possible that you could have a net magnetic field 0. So does somebody want to share theirs? I kind of would like you just simply to share your screen if you could, and that'd be faster. So the way you share your screen is at the very bottom. And if you need time to work on it, maybe you can do that now. So I'll just wait until somebody wants to share.
Mr. Lundfesty, I think I can share ours.
Sure, sounds good. So at the bottom, you'll see this little green arrow. It says share
Yeah.
screen. So just share that. And okay. So you guys said in region 4, and that's because of the right-hand rule, I think you said, right?
Yeah.
Okay, so for the wire going horizontally, imagine gripping that one so your fingers in region 4 would kind of go down in the page. And then for the wire it's going vertically, if you grab the wire in region 4, they're kind of coming out of the page. So that makes sense. Region 4, that definitely would have some region. Is there any other region, though, that you might have that?
2.
Didn't Region 2 also have one?
Yeah, region 2 would as well.
Okay.
Thanks for sharing, Brendan. Can you go ahead and unshare your page?
Yeah.
Okay, I want to talk about that one a little bit more. So, so yes, region 1 and region 2, I'm going to go see if I can kind of circle them. So region 1 and region 2 will have locations. But I want you to understand that not all locations in region 1 and region 2 have a magnetic field equal to 0. So there are still places in those regions where there would be a magnetic field. It's just that there's some locations that would have 0 magnetic field. assuming these wires had exactly the same current, so 5 amps or whatever, can you tell me what kind of geometric shape the region would have that would have zero magnetic field? Anybody?
Would it
It
be
would
a
just be
line?
a line.
Yeah, it would be a line, right? Exactly. So, in other words, all the locations that kind of are on this diagonal line would be a magnetic field of zero. And what's cool about that is, if let's say one of the wires had a current of 3 amperes and the other one have a current of 2 amperes, it would still form a diagonal line. It's just that it changes the angle. So this particular angle here is exactly at, I guess, 45 degrees from the negative x axis. But if the currents had different amounts, then it would change that angle. I hope that makes sense. Okay, nice. Thank you. Let's see, number 2. And again, you guys might need some time because I didn't ask you necessarily to have this done or anything. So for number 2, they give us wire here, W1, and they're telling us that there is a flow that is into the page of 6.6 amperes. And it says there's another wire here, W2. We want to find the direction of flow and how much flow such that the magnetic field at point P is 0. So if you need a little bit of time to work on it, so feel free to do that. And as soon as somebody wants to share, let me unshare here. As soon as somebody wants to share their screen, can go ahead and do that.
I can share my screen, Mr. Bessie.
Yeah, go ahead and take control. Okay, so let's see. Is the W1, that stands for the current then, I guess, or something?
Yeah.
Okay. So you're saying that, oh, I see what you're doing. You're saying the magnetic field from the one wire minus the magnetic field from the other wire is equal to 0.
Yeah, because it has to be equal to 0 at point P.
Okay. Okay, so you said mu W1 divided by 2.25. Now, one thing is it's really in centimeters, but the nice thing about that is it'd be 2.25 times 10 to the negative second. And eventually you set these equal, so that negative second would end up factoring out. So let's see, then what the mu's canceled. And so now you have W1 over 2.25 equals W2 over 1.5. So 6.6 over 2.2. So I think then it looks like you cross multiplied.
Yeah.
Okay, and then finally you solve by dividing. I got a slightly different number. I'm trying to, because your logic makes sense to me. I'm not seeing a problem.
I also got a different answer.
Okay, so let me run through the calculation again, but does anybody, I don't see any flaw in the logic there. The logic looks good. So 6.6 over 2.25 over 1.5. Okay, what's the problem at 6.6 times 1.5? 9.9. I agree with the 9.9 divided by 2.25. Oh, you know what? I agree everything you have there, Riley, but that last step, but when you have 9.9 over 2.25, I don't get 3.96 when I divide that. I get 4.4.
Yeah, so do I.
Okay.
I just can't plug stuff in my calculator.
Okay. So in addition, what I did was I actually kind of drew on the picture at point P from W1, I would have, by using right-hand rule, I would have a B vector, a magnetic field vector kind of pointing toward the left. And then from W2, I have to cancel that. That means there would be a B vector pointing to the right, which helps you figure out the direction. So there's one more question in this, Riley. You had to figure out which direction is that 4.4 amperes.
Wouldn't it be or because it would be that way. So it'd be up. It'd be towards 1.
Yeah,
W1, wouldn't it?
towards you. Yeah, so out of the page towards you, right? Yep. Good. So 4.4, so we agreed on that, 4.4 amperes out of the page. All right, nice. If you could stop sharing at the bottom. For number 3, I think I want to do that one because I think it might be a little bit difficult and I need to explain it. All right. So number 3 looks like this. All right, so what this is we have a wire. And in this wire, we don't know how much current there is. We want to know how much current. But we do happen to know what the magnetic field is around the wire. It's 4 Tesla and it's pointing to the right. And so in order to figure out how much current flows through the wire, we need to draw an Amperian loop around it so that we can apply Ampere's law. The truth is, when you draw an Amperian loop, you can draw it however you want. The way it's drawn here is that we've drawn an Amperian loop that is in the plane of the page. It doesn't even have to be a rectangle. It's a rectangle here, but it doesn't have to be. It could be any shape. Keep in mind, when you're doing Ampere's law, it's kind of like Gauss's law. You want to make it so it's easy to do the integration. In other words, you're not really integrating. You're just simply taking B times L. In order to do that, you need to make sure that angle's something that you could figure out pretty easily. And that's why we chose the shape of a rectangle here, because we know what the angle between the B field and that L is at any side. At the very bottom, the angle is 0. On the far right, the angle is 90 degrees. The top, the angle would be 180 degrees. And then on the far left, it would be 270 degrees. So that's why we chose a rectangle in this case. You could have also drawn an Amperian loop that is not in the plane of the page, but is perpendicular, or any angle. So there's not a way to draw an Amperian loop. You just need to make sure that you're drawing it in a way that helps you do the integration pretty easily. All right, so having said all that, all right, so to do this one, I'm going to have to use Ampere's law, which kind of looks like Gauss's law for magnetic field. And what it is, it says B dot dl is equal to mu naught times I enclosed. If you remember Gauss's law, it was the closed integral of E dot dA equals Q enclosed over epsilon naught. So it's very similar. Okay, the first thing I did was I labeled the points of my Amperian loop, numbered them 1, 2, 3, 4. I suggest that you kind of do the same thing. Okay. All right, so in order to use Ampere's law here, I need you to understand that I kind of have to break this integral up into 4 different sections. And so I've made it like this. I'm going to integrate B dot dl from 1 to 2, then from 2 to 3, then from 3 to 4, and then finally from 4 to 1. Sometimes students forget to do the 4 to 1. You have to have a completed loop. So that's the same statement as up above. The other thing you have to understand is that that dot product there is actually going to be this B times L times cosine of the angle between them. Why did I put it there twice? Don't know why I put it there twice. Sorry about that. Okay, so for instance, that first integral there, that would be B times the length from 1 to 2 times the cosine of 0 degrees, which that's nice, that's just 1. And for the next one from 2 to 3, that would be B times the length from 2 to 3 times the cosine of 90 degrees. It's always the angle between the B field and the path that you're moving along. For the next one is B times the length from 3 to 4 times, in this case, the path you're moving is to the left, but the B field's to the right, so the angle would be 180 degrees. And then finally, the last one is going to be B times the length from 4 to 1 times cosine of 270 degrees, because the path is moving straight down, but the B field's to the right. You'll notice that the B field here was constant. That's why I was able to kind of factor it out of the integral. And when I'm just integrating the integral dot d, or just the integral of dl, that's just simply the length. So I know what the length from 1 to 2 is. It's 1.2 meters. I know what the length from 2 to 3 meters, or 2 to 3 is. It's 0.5 meters, and so on. But some of this drops out. For instance, the 90-degree term and the 270-degree term, those two are going to drop out. Those are 0. And the third term with the 180 degrees, that's going to be a -1, whereas the cosine 0 is 1. So if you do all the computation here, how much do you get on the left-hand side?
0.
You get 0. So my question is this: how much how much flow is going through that wire? If this is all 0 on this side, how much enclosed how much enclosed current is moving through the wire?
0.
Yeah, it's 0. It's 0. So we used Ampere's law to prove that there is no current in that wire. You might think, well, how is that valuable? Well, it's kind of like what we were doing the entire first semester. We were using a compass to determine whether there was a flow through that wire. This is a mathematical way of the same thing that we were doing with the compass. Okay, so any questions about that one? So the agreed upon answer here is that the amount of enclosed current is 0. All right, so then the next one we're going to look at is number 4. Number 4, we want to figure out what the magnetic field is at some distance, 1.2 meters from the bundle. So my suggestion here is to draw an Amperian loop that kind of reflects the symmetry. So that would be kind of a circle. And I'm going to make it kind of dotted here. And so we're going to be going around this bundle of wires all the way around it. So they're kind of right in the center of this. And we're going to use Ampere's law. Maybe I should go back to here. Ampere's law, that's this equation. I wonder if it'll let me paste it. Nope. Darn. Okay, so anyway, you're using Ampere's law. Oh, I know, I can do a picture of it, screenshot. Snip. Give me a second here, sorry. There we go. So you're going to use Ampere's law then to figure out what the B field is at some distance away. So how about I give you a little bit of time if you need it for this one. And then as soon as somebody has something they think they feel pretty good about it, then go ahead and share it with us. This is number 4. If somebody has it, you can go ahead and take control whenever you want. Okay. All right, so we kind of use Ampere's law here. Let's see. Okay, so I think the calculation we're showing here is for the, oh, I see what we're doing. You actually, okay, I didn't even think about this. So what you were really doing was you looked at each one and you found the B field from each one. I think that's what you did. Is that right, Josh? Or is this Riley? Who did this one? Oh, this is Josh. Can Josh talk or no? Josh is quiet. No, he can't talk. Okay. So it looks like he found the magnetic field from each one of the wires. For the first wire, that he's saying up upward, that's going to be a positive. He's calling that positive. And then for that, that next wire, 3, that's also positive. But then his last calculation there, that would be for 2, which is in the opposite direction. And so that's negative. And so when he figured out the total magnetic field there, he got 0. And I agree with that. I kind of want to show how to do that, though, also using Ampere's law. So that way works as well. So I'm going to go ahead and see if I can take control back. Okay. So for this one, if you're using Ampere's law for this, the I enclosed, if you're looking at it, you have I1 and I3 both going in the same direction. And so that would be 1 plus 2, that would be 3. And then you have I2 going in the opposite direction. So that would be kind of like -3. So the I enclosed would be 0. So using Ampere's law, the right-hand side would be equal to 0. And you get that kind of quickly. And then solving that for the magnetic field, well, that must also be 0. So I think it's a little bit quicker that way. But your way works too. That's the first time I've seen it that way. That's kind of interesting. I like that. That's nice. Different. Okay, let's see. I think maybe we'll do one more. Number 5, a conventional current flows through a conducting hoop as shown. Draw on the magnetic field lines with arrows. And then figure out which side of the hoop is north. So this is more of a conceptual question using the right-hand rule. So if somebody would like to share theirs when they get that.
I can.
Okay, go ahead and take control.
You're still screen sharing, so
I
I
am?
can't.
Oh, sorry. There we go. Okay, so using the right-hand rule, we kind of grip the top up there, and you would have to have your thumb coming out, your right thumb coming out towards your eyeball. And so then thinking about how your fingers curl through it. It's not so much on the outside, all that's nice. I like the way you've drawn that too. But on the inside, notice your fingers are kind of curling into the left-hand side and they're coming out the right-hand side. You could also done the same thing at the bottom. Notice the flow is in on there. So you would do the exact same thing and you have the same direction for your flow. And so that means you're saying the right side is the north side of this. Sounds good to me. Any questions on that one? All right, thanks for sharing. And if you could unshare, and I think that's all we're gonna do today, but I do wanna talk about some of the other problems to help you out with this a little bit. I think I'm gonna come back to this one real quick so I could still Ampere's law. Oops, that wasn't it, wrong one. Ampere's law, number 4. You steal this equation. Okay, so we just did 5, and look at 6. Okay, to do these other problems, starting with like number 6 here, is you have to draw Amperian loops. In fact, they've been drawn in for you to help you imagine this. So here, have this wire, and it's kind of coming toward you three-dimensionally, and you've got this flow in the wire that's coming toward you, and there's 2 different regions that we want to know the magnetic field. We want to know the magnetic field outside the wire. So that's that bigger Amperian loop. And we also want to know the magnetic field inside the wire. Well, in order to figure out the magnetic field inside the wire, that's the harder part. You have to realize that not all the flow goes through the Amperian loop. And so in order to figure out the amount of flow that goes through the loop, you're going to have to do a proportionality using the area of the loop compared to the area of the wire itself. So that's kind of your hint for that one. Okay, it's similar to some of the stuff we've done with Gauss's law, but in my opinion, it's a little bit easier. Number 7 is similar to the lab. By the way, some people haven't sent me the pictures of their lab yet. That's fine. Just, get that to me today. Okay, that we whiteboarded already. Number 8, in fact, I think I want to go to number 8 really quickly because it's a little bit tougher one. Okay, same idea for this one. This is another kind of wire that's got a bunch of curls in it, and so we have a flow through it. But then on top of that, it's been bent around back on itself, forming this kind of slinky that's kind of getting ready to touch ends together. And we want to know the magnetic field in a couple different locations. Outside it, they're calling that path 2. And actually inside it, and it's hard to see that one, that's path 1, that's inside the actual slinky. There's one more place where it wants to know. It says, what would the magnetic field at the center of the toroid be? So they didn't draw it here, but I'm going to draw it real quick. You could draw one more Amperian loop in here to answer that, okay? In my opinion, that last one's probably the easiest one. Probably inside the slinky is also somewhat doable. It's not that hard. Probably the hardest one is path 2. What you need to think about is, imagine you can cut the slinky in half and you can see one wire. You'll see these 2 different spots where you're cutting in half. And one side of the wire, you're seeing the flow go into the page. The other side of the wire is coming out of the page. So you really need to think, well, how much total current does it enclose then, right? Okay, and I think that's all I'm going to say about that. And I don't know if I'm really going to talk about number 9. Okay, next thing I want to talk about, and this is going to be the remaining amount of time, is, so let me get out of these, is I kind of want to talk about the lab. I would like you to get data for a lab, and then we'll whiteboard it after we come back from break. But the directions for that are here. Actually, before I get in the lab, maybe I need to share with you what I thought was kind of interesting. So this kind of got me thinking. Can you guys see? I wonder if you guys can see what I see or not. Let's see here. No, that didn't work. Okay. Oh, wait a second. I got to get rid of my background. Sorry. Hold on a second here. I got to stop sharing for a second. Got to get rid of my background. Later, Dunder Mifflin. All right. Okay. So now I need to share again. All right. Okay, so I'm hoping that you can see I kind of have the circuit set up. And I've got this switch here that when I close it, you can see the light bulb come on, right? So this is what it got me thinking. You know how that the first semester we use a compass, and the compass helped us figure out if there was a flow through the wire, right? Well, we now know a compass is basically a magnet, right? So that means this wire creates this magnetic field. And so I started thinking, given that one magnet can affect another magnet, I kind of wondered what would happen if I brought a magnet near the wire. Okay, so I want to show that. So here's a magnet, and can you guys see that? Yeah, you can see it. So I got it near the wire, and you don't really see anything, right? I'm hoping you don't see anything. But notice what happens when I close the switch to the wire. So watch the wire. What'd you see? What'd you see?
The wire moved.
Okay, the wire moved. So there is an effect here. And there's one more thing I want you to notice. Now I'm going to flip the magnet over. So notice which way it's moving. I'm going to flip the magnet over. What did you notice?
It moved the other direction.
Moved the other direction. So in other words, it looks like there's a magnetic force on this current carrying wire. When I've got the magnet here near the wire, they're really, if I don't hit it, there really isn't any motion or anything in the wire. It's only when there's current flowing through the wire that there's some kind of magnetic force on it. So I kind of want to figure out what's the relationship between that magnetic force and, well, what do you think might affect that magnetic force? What factors?
How far away the magnet is?
Okay, so what is that affecting exactly? What are you saying that's affecting?
Distance.
I get the distance, but
Like the distance the magnet is from the wire affects the deflection of the wire.
okay,
The wire
which would be how much force, right? But I think what you're saying is by moving it further away, so try to imagine the magnetic field coming from it. As I move it further away, you're saying that the magnetic field is smaller or something like that. I think that's what you're saying, isn't it?
Yes.
Okay, and I can kind of show you that too. So I'm going to go ahead and do it with this. I have a big magnet here. So this is the big magnet. Now I have a smaller magnet. I don't know if you can even see it here. Wait, there we go. Smaller magnet. I don't know. Could you even see it move? I can see it move. It does move a little bit, but not much. So I think that's a good idea. I think that instead of saying distance away, though, I'm going to say strength of the magnetic field. It's kind of the same thing. So strength of the magnetic field, I agree. Anything else?
Flow.
The flow. Let me see if I can prove that to you as well. So right now there's a certain flow. Oops, I think it flipped around. Sorry. There's a certain flow through the wire. But I could increase the flow by just getting rid of the resistance, right? If I get rid of this resistance and connect it like this, so that way we won't see the light bulb come on now. Okay, so keep that in mind. Can you see it's quite a bit more? Quite a bit more compared to that. So I agree. I think flow, so magnetic field strength, flow, anything else you could think of? Okay, this last one I think is hard, so I'm just going to suggest it. I think it might have something to do with how long the wire is. The longer the wire, I think the more force maybe, but not necessarily. I think it's kind of hard for me to prove that here with what I have. Sorry. So let me show you what we usually do in lab. What we usually do in lab is the following. And it kind of makes me sad because I just put a whole bunch of money in for this lab, but that's all right. So it's hard. Okay, so I made these devices myself, and all this is PVC with 2 pieces of iron up here, and I've got magnets here that you can actually take off. By putting more magnets or less magnets on here, you can change the strength of the magnetic field. Does that kind of make sense, I hope? Yeah. And what we do is we hang wires. I don't know if you can see this wire here, but we hang wires like this, and we can actually cause there to be a force on this wire. And this is a certain length. This would have a different length going through here. Sorry about that, smaller length. And I had a whole bunch of them. I had like 6 different lengths. And also you can vary the current to see how much flows through there. Now you might think, well, how do we measure that force? Glad you asked. What we do is, this is where I spend all the money. I bought some electrode imbalances like they have in chemistry, except these are super precise. They go to like 1,000, 10,000 gram. Anyway, this sets on that triple beam balance. And because of Newton's third law, yes, there is a force on the wire, on this wire, but there's also a force on the magnets. And so what you'll see on the digital balances, you'll see the weight of this appear to change. So it's kind of cool. kind of wish that you guys could do it. So you're going to have to do it virtually. So I want to share with you what the lab looks like. All right, let me show you the lab here. Okay, so first of all, I need to give you some information about the lab. Let me open this up. The website, and I'm going to show you the website here in a second, is called Pivots Interactive. Show you where it's at. The first time you log in, you join, you'll have to give this class code. And I went ahead and assigned this lab. But I think I want to skip over this, although you should read this right here. I'm not going to go through it with you. I want you to see that I've given you some groups. So some of these groups are the same, some of them aren't the same. But specifically what I want you to see is for the 3 different parts of the lab, where we're looking at the effects on the magnetic force from the current, from the length, and from the magnetic field strength. I want you to make sure these groups are using whatever these constants are. Like they have different conductors, so make sure like this first group here is using conductor 1, and they're using magnet A. And then for part 3, you'll use magnet A, and you can have your current to be whatever you want it to be as long as you don't change it. And for the last part, you'll use conductor 1 again, and you can have your current be whatever you want it to be as long as you don't change it. So that's kind of the thing I want you to see, and it talks about after the lab and stuff. So this won't be until after we come back from spring break that you're sharing this, so you should have plenty of time for this. Okay, now let me show you what the lab is at Pivot Interactives when you go there. So it's kind of like the setup that I was explaining to you that we had in classroom. So there is a magnet here. We have a wire. The wire goes from this red wire all the way across over to the other side, to the left side. And that's going to have an effect on this scale, the spring scale. So instead of just talking about it, I think I want to show you. So the way these Pivot Interactives work is there's a video, and you can play it. And so you can kind of see there from Newton's third law what happened there to that force. Again, there's a magnet back here, and there's a wire kind of right near it, and it feels this force, and it causes the deflection. So you'll notice here that you can change things, like you can change the direction of the magnetic field, you could change the direction of the current, but after you change them, you have to hit go. Okay, and then you can play it and see what happens. And you might see something totally different. And realize to get your data, you're probably going, because it's bouncing around a little bit there, you're probably going to want to find where it's not bouncing it anymore. After you've connected it, it's not bouncing. And you might have to zoom in to read that. Okay? So just be careful there. And also notice it says it's in grams. So to figure out the force, you're going to have to figure, what that would be. By the way, I probably should mention this. You don't need to fill all this in. All I want you to do is get data, but you really need to understand how this equipment works. So for this number 1 up here where it says something, I even ask you a question like, it says on the video below, select the magnetic field pointing inwards and the current to the left. What is the magnetic force? You should go ahead and do that calculation, because if you get the calculation wrong, that will tell you that you don't really understand what this equipment's doing. So you should really take the time to understand it. By the way, it gives you the answer right down here, so you can see if you understood it or not. There's some other things that I want you to see that you can do over here. Like you can plug it, you can kind of use your right hand rule to figure out stuff or whatever. So there's little tools on here. This is just understanding the equipment. For doing the lab, for force versus current, for instance, it tells you stuff about the magnetic field. Don't forget that some groups are going to have a certain magnet, a certain conductor. So let's say your magnet is magnet A, but let's say you're doing conductor 2, you would have to hit go before you collect your data. when you get your data, again, try to get 6 data points or as many data points as possible. Don't put it in these columns because you're not turning anything in here. You're just getting the data here. Okay. Any questions? Okay, well, that's kind of the assignment. So there's 2 assignments. I need you to then, because we're kind of done, I want you to take the attendance quiz. It shouldn't take very long. You're just going over those answers. Submit those and then start collecting the data here. Maybe share a Google Sheet with your partners so that you can maybe divide and conquer it a little bit so you don't have to do all the work yourself. Okay. All right, that's it. Hope you have a relaxing spring break.
Bye, Mr. Lenfesti.
Later. Bye.
See you, Kenzie.
What's he doing?
See you, Kobe.
See ya, Tay Tay.
Randy, your brother's on there.
Noticed.
She gave me the link.
I did notice. Did you get to see my Dunder Mifflin thing anyway?
I did see that. Yeah, I've just started watching The Office, so that's pretty good.
Oh, good. So, bye, Mark. All right, see ya. Y'all good? Okay. All right, see ya. Bye, everybody.
Bye, Mr. President.